Okay, good morning. Today our agenda is to do three things. The first is to talk about how we kind of have two equations for the gravitational force. We have this mg thing, and then we have this gmm over r squared r hat thing, minus sign. And how are they related? How can there be two equations for one force? I'm going to talk a little bit about, talk about superposition when there's more than one object in the surroundings exerting forces. I want to talk about the electric force, which is similar in mathematical form and in distance dependence to the gravitational force. And then come back to why momentum is important. Talk just briefly about the idea of conservation of momentum, which is one of the strongest principles, forms of the momentum principle, and involves systems with more than one object in them. So that's the agenda for today. Please do type your name in chat if you haven't already. So to review briefly, we talked last time about the gravitational force, where if we have two objects, 1 and 2, that have some masses, m1 and m2, that they're attracted to each other by the gravitational force, and that we can write the gravitational force, which has both a magnitude and direction, of course, as a minus a constant g, mass of object 1, mass of object 2, the square of r over the magnitude of r squared r hat. And what does this actually mean? Well, it depends on what we have to choose. One as the system and one as the surroundings. So if we choose this as our system and this is our surroundings, then we want to calculate the force onto by 1. So we would draw our vector r from the object in the surroundings to the system. So the vector r is a relative position vector. It's the position of the system relative to this particular object in the surroundings. And so this is force on to by 1. And therefore the vector r hat is going to point that way. And since mass is positive and distance squared is certainly a positive number, that's going to give us a force pointing that way. And we calculated gravitational forces in recitation. On the other hand, near the Earth's surface, though, we've used the gravitational force was equal to 0 minus the mass of the object times this constant little g, 0. Oh, for completeness, we should write that this big constant, big G, is 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. And this little g thing was 9.8 newtons per kilogram. So it doesn't even have the same units as this constant big G. So where does that come from? And really where this comes from is actually, it's a special case of our general equation. So this equation actually comes from that equation. And the idea behind it is that if an object, the Earth has some radius r of the Earth, this is the Earth. And that's a big number. Actually, the radius of the Earth is about 6.4 times 10 to the 6th meters. So if you're anywhere on the surface of the Earth, whether you're here or here, or you're actually 1 meter away from the surface of the Earth or 2 meters away from the surface of the Earth, so on the Earth's surface, our Earth plus 2 meters, say, really isn't very different from the radius of the Earth. We're adding 6.4 times 10 to the 6th meters plus 2 meters. And that's pretty much equal to 6.4 times 10 to the 6 meters. So we can say that as long as we're near the surface of the Earth, not very far away from it, the distance from the center of the Earth is approximately the same. It's approximately the radius of the Earth. Now, why are we talking about the center of the Earth? Well, it's a fact that we can show mathematically using calculus that that if we have a solid sphere, or actually if we have a solid sphere of uniform density, it's made up of lots and lots of atoms that are in different places. So you'd think that the force on some object over here would actually depend on the location, the different locations of all these atoms. So we'd have all these different distances. But it turns out that if you add this up mathematically using calculus, you get the result that its interaction is exactly the same as if Superman had come along and squashed this big solid sphere down to a tiny, tiny point mass at its center. And that's because it's because the force goes like 1 over distance squared, but the volume of a teeny slice here, the area of a teeny spherical shell goes like r squared. And so in fact, if you add that all together, it ends up looking like a point at the center. So we can say that when we're talking about masses interacting gravitationally, we can model them as points at their centers with all the mass concentrated in that little point. So what would the magnitude of a force on some object at the on the Earth's surface be? Well, it would be approximately g times the mass of the object times the mass of the Earth over the radius of the Earth squared. And if the object had some other mass, the only thing that would change in this equation is the m. So we can rewrite this as the mass of our system times the quantity g, mass of the Earth, radius of the Earth squared. And what do you think this comes out to when we actually calculate this? This is going to be equal to the mass of the system times 6.7 times 10 to the minus 11 Newton meters squared per kilogram squared. The mass of the Earth is 6 times 10 to the 24 kilograms. Yeah, the radius of the Earth is 6.4 times 10 to the 6th meters, and we're going to square that. And that just comes out to be equal to 9.8 newtons per kilogram. And that's, so we call that little g. So this quantity here is equal to little g. So we could make that calculation on any planet or comet or asteroid or whatever. Instead of the mass of the Earth or the radius of the Earth, we'd have to use the mass of the object and the radius of the object, right? And so we'd get little different values for little g. Now, little g is an approximate value for two reasons. The the distance from the Earth. I mean, on top of Mount Everest, you're farther away from the center of the Earth than you are in Death Valley. But the other reason is that the density of the Earth varies. And so, in fact, little g, the field of the gravitational field of the Earth, isn't exactly 9.8 almost anywhere on the Earth. And in fact, prospectors who are looking for mineral deposits or oil deposits or whatnot will sometimes actually measure the value of little g at their location as to see if that's an indication that there's something interesting below the surface of the Earth. So let's see if we can reason about this a little bit. So here's a question. Suppose we're on Mars. So the mass of Mars is an order of magnitude smaller than the mass of the Earth. It's 6.4 times 10 to the 23 kilograms. Its radius is smaller than the radius of the Earth. Okay. All I have is a poll with 4 alternatives, so don't answer 4. So here's a question. If the Mars rover measured the value of g on Mars, would it be equal to 9.8 newtons per kilogram, smaller, or greater? Okay, let's see what you said. So the biggest majority votes for 2 would be less than 9.8 newtons per kilogram. A few people said it would be greater. So let's see what we get here. Let's see if we can estimate it. So for Earth, little g is g times mass of the Earth over radius of the Earth squared. Mars, little g is equal to, this doesn't change. We have something that's roughly 1/10 of the mass of the Earth here. And then we have something whose radius is roughly about 1/2 of the radius of the Earth squared. So that looks like it's going to be equal to 1/10 over 1/4 times the mass of the Earth over the radius of the Earth squared times g. And so that looks like it's equal to about 0.4 times little g. Now we need to take into account both the radius and the mass, right? So here's a question. If we have planet A with a mass of 4 times 10 to the 23rd kilograms and a radius of 3 times 10 to the 6 meters, planet B has twice the mass and twice the radius, so it's bigger in both dimensions. Which planet has a larger value of g? Yeah, so that's exactly right. You need to really remember that we have that r squared in the denominator. Well, Answer 2 is more popular, but answer 1 is also popular. If you said they're the same, you're probably not thinking about the fact that the radius is squared. So let's see how we let's do one more example of this proportional reasoning, which is so important in these cases. So for planet A, we'd get G times, we're going to ignore the powers of 10 because they're going to cancel out, 4 over 3 squared. So we get 4/9 times G. Planet B, we have G over 8 times 6 squared, which is 8/36 G. So 4/9 is about a half, right? So that's roughly a half G. And this is a little bit less than a quarter, so it's a little bit less than a quarter G. So in fact, looks like it's bigger on planet A because the radius is in the denominator. And if you square the radius, you're dividing by a big number, so it makes the overall number smaller. So the fact that you're squaring the radius really makes the difference here. Okay. So now let's talk about what happens when you've got more than one object in the surroundings. So superposition. Superposition of forces means that we've talked about this before, that to get the net force on something, you just add up all the separate forces acting on it. So in this case, it says F net is the sum of all the individual Fi's from surroundings. But it also says something else. So we've already seen that. It says that each of these individual forces is unchanged by the presence of other objects in the surroundings. So here's an example. Suppose we have a binary star, star 1 and star 2, orbiting each other. And this turns out, astronomers are finding more and more of them. It turns out to be a really common situation. But let's imagine that this this binary star has a planet. And we want to get the net force on the planet. Well, we would simply say, okay, we want the force on the planet due to star 1. And we get the force on the planet due to star 2. And then we add those vectors by putting them tip to tail to get the net force on the planet. So nothing new there, except for the fact that star 1 exerts the same force on the planet as it would if star 2 isn't there. The fact that star 2 is also exerting star 1 is also exerting a gravitational force on star 2. Gravitational force doesn't get used up. Okay, it's just a property of the masses. So that this force, if we just had star 1 and our planet, this force F1 has the same magnitude in both cases. And it's also true that it doesn't matter if things are in the way. Okay, forces go right through these distance forces go right through matter. So suppose we had star 1 and star 2, and here's our planet. Well, here's the force due to star 2. And now to get the force due to star 1, we just pretend star 2 is not there and calculate the force due to star 1. It's going to be smaller because even if these stars are equal masses, say, because it's farther away, so we're going to get an F1 because it's farther. But forces go through matter. So the fact that star 2 is in the way doesn't affect the force that star 1 is exerting. And you see examples of that all the time in your daily life. The fact that you've got a table in the way doesn't change the fact that the Earth is pulling down on your computer. Okay, so the force due to the Earth is going right through your table. And the force the Earth is exerting on you is going right through the floor. It doesn't matter that the floor is in the way. So these forces go through matter. And of course, what can we do with these forces? Well, we can use them to update momentum and update position. And we saw some time ago in lecture a simple example of using the model of the sun and the Earth to predict the motion of the Earth by just calculating the gravitational force the sun exerts on the Earth, using that to update momentum, taking some time step delta t, using an approximation for average velocity as momentum over mass, getting to a new position, recalculating the gravitational force and doing it again. So we're doing the same iterative update at all times. The only difference between this and a constant force is that because the direction and magnitude of the force changes as the positions change, we have to go through we have to recalculate the force each time. We have to go through calculating a new r vector and then a new gravitational force and then a new delta p. Otherwise, it's exactly the same thing. So that's gravitational forces. So Brian says, do other planets in our system not factor in for Earth because the sun is so massive? So that's a really good question. And the answer is the effect of the sun is so massive that is by far the predominant effect. But in fact, if you were making a realistic model of the Earth's motion, you would indeed have to include the other planets because their effect is not zero. That's one of the things that perplexed the earliest cosmologists. Before Isaac Newton figured out the gravitational force law, people didn't understand why these orbits weren't entirely perfect circles. And the answer is that the other planets do interact and do affect each other. In our simple model, we neglected that. And in fact, it turns out that the Earth's orbit is not quite circular, but it's really close to a circle. So it's just a slight bit elliptical. It's not a perfect circle, but it's very close to a circle. So our simple model does pretty well, just because indeed, as Brian said, the sun is so massive that it has the dominant effect. So part of what goes into building a model is to make a guess at what you think the dominant interaction is going to be, build that in, see if you get roughly the behavior you expect, and then refine it by adding in other interactions. So that's basically the process. So we've talked about the gravitational force. There's another force that looks very much like that mathematically, and it's the electric force. The electric force is another one of these fundamental forces. Any object, any particle that has what we call an electric charge can interact at a distance with any other particle that also has an electric charge. And you know from chemistry about the most familiar particles that have electric charges. You know that atoms are made up of protons, neutrons, and electrons, that protons are positively charged, that electrons have what we call negative charges, and neutrons have zero charge. They don't have an electric charge. Now, the electric force is actually more varied and interesting than the gravitational force because it's not always attractive. So, in fact, it can be attractive or repulsive, and it depends on the sign of the charge. We call these charges, the charge is a physical property, but we call them positive and negative because we're representing them mathematically by positive and negative numbers. And these signs actually do a good job of allowing us to represent this force algebraically. So the things we want to capture about this force are that two positively charged objects actually repel each other. And two negatively charged objects also repel each other. So this is repel. Repel meaning, well, what you think it does. If we put them down close to each other and let them go, they'd move away. But a positive charge and a negative charge actually attract each other. And so, so our assignment of these signs to it is an attempt to capture this behavior mathematically by making the direction of the force come out right in our equation. Now, there's some values we need to know. The unit of charge in the SI system is Coulomb, named after a French physicist. Abbreviated with a capital C. And we find that in our observations of the microscopic world, that charge comes in quanta, in little packages. So the smallest amount of charge that we ever find on something is the charge on a proton. And the value of that is 1.6 times 10 to the negative 19 coulombs, which tells you what a big number a coulomb is. And we use the mathematical symbol of lowercase e for this, as if we weren't using it for other things. But there it is. So in this case, the number e has the value of plus 1.6 times 10 to the minus 19 coulombs. The charge on an electron is equal to minus e, so it's equal to minus 1.6 times 10 to the negative 19 coulombs. And the net charge of an object you just get by adding up all the charges. So if you had one proton and two electrons, so looks like an H minus ion, not very stable, but if we did, its net charge would be plus E plus a minus E plus a minus E would give us a minus 1.6 times 10 to the minus 19 coulombs. And we often use, so E is a constant. We often use the symbol Q to mean the amount of charge on a chart that a charged particle has. And this is a scalar, but it has a sign, so it can be positive or negative. Let's write the equation for electric force. So let's say we have particle 1 with charge Q1 and particle 2 with charge Q2. And we're going to take Q2 as our system. So this is part of the surroundings. Then the electric force on 2 is equal to a constant, and it has the same form as the gravitational force. So it depends on the charge of particle 1, depends on the charge of particle 2. We have a magnitude of r squared and an r hat in the r squared in the denominator and r hat, and there's a constant which is written as 1 over 4 pi times epsilon 0. So epsilon 0 is a fundamental constant, and we write it this way rather than just calling it K, because way too many things are called K. Spring stiffness is called K. There's lots of other constants called K, and because this value epsilon 0, as we'll see really next semester, has a life of its own and an importance of its own. And so this whole constant here, this 1 over 4 pi epsilon 0, has the value of 9 times 10 to the 9th Newton meter squared per Coulomb squared. So the gravitational constant had units of Newton meters squared per kilogram squared because mass was the operational thing. And here this has units of Newton meters squared per Coulomb squared because that's the operational thing. Now, where does the direction, and of course the vector r, as usual, goes from the surroundings to the system. So where does the direction of this force come from? Now notice there's no minus sign here. The direction comes from the direction of r hat, of course, and then the signs of both of these charges, because there can be pluses and minuses in here that can, when we're multiplying a vector by a plus or a minus, that can change the direction of the vector. So all of these three things contribute to the direction. Well, E is not the minimum charge of a proton. All protons have exactly the same charge. So E is the charge of a proton. What it's the minimum of is that we never find a particle sitting around by itself that has a charge smaller than either plus 1.6 times 10 to the minus 19 coulombs or minus 1.6 times 10 to the minus 19 coulombs. So the absolute value of the charge on any particle that we can detect by itself is that value, E. Let's do a calculation, okay? Well, let's just see what happens here about directions. So let's say that we have, let's say Q1 is positive and Q2 is also positive. And we're using Q2 as the system here. So we've got here's our vector r, and we have r hat here. And this should be a repulsive force, so we want the force to end up going in that direction. So if we take this as the x-axis, then it should be in the plus x direction. So let's see if that works out. In our equation, we have a 1 over 4 pi epsilon 0, that's positive. We have a q1, that's positive. We have a q2, that's also positive. We have the magnitude of r squared, that's positive. And so we're multiplying r hat by a positive number, so the force will be in the direction of r hat. So the force will indeed be in the direction. In this case, by inspection, we see that r hat is equal to 1, 0, 0. What if they're both negative? So if they're both negative, we have a negative and a negative. R is still the same. We still expect a repulsive force, so we still expect the force to go that way. And what we've got here is 1 over 4 pi epsilon 0. That's 9 times 10 to the 9th, so that's positive. We have q1, which is here. q1, which is negative. We have q2, which is also negative. Magnitude of r squared is positive. R hat is 0, 1, 0. And if we multiply two negative things together, we get a positive number. So in fact, this comes out to be positive, and we do indeed get a force in the direction of r hat, which is okay. So the remaining case is if one of them is positive and the other is negative. And now we still have r going that way and r hat going this way, but we think the force ought to go in the minus x direction because it's attractive. And we have the forces 1 over 4 pi epsilon 0 q1, q2 over the magnitude of r squared, r hat. q1 is positive and q2 is negative. So this product is going to give us a negative number. So we're multiplying r hat, which is 0, 1, 0, by a negative number. And so we actually get a direction in the minus x direction, which is correct for the force on the negative object. So let's say if we had a chloride ion at location minus 2 times 10 to the 9th meters, 3 times 10 to the 9th meters, 0. And we have an alpha particle. An alpha particle is a helium nucleus. So it's got 2 protons and 2 neutrons, but it doesn't have any electrons. And alpha particles are emitted in some kinds of radioactive decay. And that's located at 5 times 10 to the minus 9th, negative 1 times 10 to the minus 9th, 0 meters. We want to find the force on the chloride ion by the alpha particle. So really all we need to do is calculate the vector R. And since the chloride ion is the system, yes, the system, because we want the force on it. The alpha particle is part of the surroundings. The vector R is equal to the position of the chloride ion minus the position of the alpha particle. And then we just plug and chug. And of course, the way I recommend doing this is by using Python. So let's do it that way. So we're going to need the constant. So 1 over 4 pi epsilon 0. A student invented the symbol for it of using the first letters of all those words. So 1 over 4 pi epsilon 0, or UFPES, and I like that so much that I use it. So that's 9 times 10 to the 9th. The charge of the alpha particle is 2 times 1.6 times 10 to the minus 19 coulombs, because it's got 2 protons and no electrons. The charge of the chloride is equal to negative 1.6 times 10 to the minus 19 coulombs, because a chloride ion has an extra electron. A chlorine atom is neutral, but a chloride ion has gained an extra electron, so it's net charges. The position of the alpha particle, yes, real charges will often always be in multiples of 1.6 times 10 to the minus 19, but when you get an object of ordinary size that's not a proton or an electron or a single ion, you can have a lot more charge than that. And so, if you, for example, rub a balloon on your sweater, it gets charged, and we'll talk about that next semester. It can have charges on the order of a nanocoulomb, on the order of 10 to the minus 9th coulombs, which is just a lot of excess electrons or deficiency of electrons. So the location of the alpha particle we decided was 5 times 10 to the minus 9, 1 times 10 to the minus 9, 0 meters. And the position of the chloride ion is a vector negative 2 times 10 to the minus 9, 3 times 10 to the minus 9, 0 meters. And now we're ready to go. So R is equal to, we want the force on the chloride ions, so that's R chloride minus R alpha. And now we can actually just put it together. So we have the electric force on the chloride is equal to the constant 1 over 4 pi epsilon 0 times the charge of the chloride ion times the charge of the alpha particle, divided by the magnitude of R squared. And the reason I don't need parentheses here is that the magnitude operation is taken before it's squared. And then we have to multiply this whole thing by R hat. Well, I mean, so if you're interested in questions of how they choose the units the way they do, first of all, they have to be consistent throughout the whole system. So back in the day, before we all agreed on SI units, there was a system called CGS, centimeters, grams, and seconds, and they used a different unit for electric charge. But to be consistent, for everything to work out in a consistent way, this is what a coulomb turns out to be. So that's what it is. The typical charges we measure are much greater than the charge on a proton, but they're not. A coulomb is a lot of charge. So 10 to the minus 9th coulombs is a charge that you might expect on an ordinary object. And so now we can print our force. And if I did this correctly, which we'll see, we get a number that is on the order of 10 to the minus 12 newtons. And again, let me point out that that this was an extremely easy way to do it, because otherwise you would have had to do this vector subtraction by hand, and then to get the magnitude, you would have had to take all the components of these, square them, add them up, take this, get the square root, then divide the vector r by that to get r hat. So VPython is your friend. Now note also that the principle of reciprocity that we saw yes, you'll have a glow script trinket embedded in a non-question on the test, the way they have been on quizzes. So you can use it in tests. And I will. Yes, that's right, Morgan. I multiplied the charge of the alpha particle is 2e because it has the alpha particle has 2 protons, 2 neutrons, which has a charge, and no electrons. So we're adding that up to get the net charge. So we have 2 positively charged particles and 1 negatively charged particle here in this diagram, and we're going to assume that the positive charges have the same magnitude, the same amount of charge. And so our question is, what is the direction of the net force on the negatively charged particle? So there's a question about superposition, about adding up forces. So almost everybody said 7, and that is exactly correct. So good for you. The way it works is that we have to take these one by one. What we're doing is superposition of forces. So the force on the negative charged particle by the top positive charge is going to be that way, because they're opposite charges, so they're attracting. The force on the negative charge by the bottom particle is that way. And if we put these vectors tip to tail, we get a net force in that direction. Okay, let's try a more interesting one. We still want the net force on the negatively charged particle, but this time it's in between two equal positively charged particles. And you said overwhelmingly 7. And that is also exactly correct, so good job. And this is somewhat more interesting because both of these both of the red positive charges attract the negative charge. So the force, we'll call that F left, due to that positive charge is to the left. We'll call this L and that one R. the force due to the right one is to the right, but it's much smaller, isn't it? Because it's much farther away. In fact, it looks like it's at least twice as far away. So if we say it's twice as far away, the force would only be a quarter as large. So that we have to add those two vectors, and remember, we can add vectors that are, so here's F left. We put the tail of the other vector at the tip of this one. I'm just going to draw it a little bit offset so we can see it, F right. And so the net force is to the left, but smaller. So Hunter's invented a problem where we put the two positive charges equal distances from the negative charge. And in that case, her guess is exactly right. We'd have a force, an attractive force to the left, an attractive force to the right. They'd be exactly the same magnitude, so they'd add up to 0, and in this case, F net would be 0. So, great thinking. Okay, Parker's saying that the positive particles would experience forces too, and that, of course, is correct. So what we're doing again is we're doing this physics thing of taking a snapshot of something at an instant. We're asking about the forces at an instant. So it's true that in any of these situations that we drew, where we had even the first one where we had positive charges here and a negative charge here, okay, so Michael raises an interesting question. So let's go back to the first situation. We chose a system, so we chose the negative charge as the system, and we worried about the net force on the negative charge, which was that way. Now, if we chose something else as the system, and it's at this instant, so at any instant, particles are where they are, and the force is what it is. And so we're always calculating force at an instant. And if we want to predict the motion of a system into the future, remember that we use that force for only a tiny time step, small delta t, and then we decide we need to recalculate it because the forces may have changed because particles have moved. Now, these particles, these positive charges do experience forces. So this positive charge will be attracted to the negative. It's going to be repelled by this other positive charge. And so the net force on this guy is going to be something like that. And likewise, the net force on this one is going to be something like that. So if we wanted to predict the motion of this whole system, we'd have to calculate all these forces, and then we'd have to use these forces to update the momentum of each particle one by one and update their position using that new momentum. And then they'd be in new positions, and we'd have to recalculate the forces and do it again. So it'd be complicated. So anytime we ask for a force, we're assuming that we're talking about some particular instant because it only makes sense at some instant. So Alexander, in this problem, the y components of the forces on the negative charge canceled out, but the y components of the forces on these positive charges didn't cancel. So we still have to add. Now, Michael raises an interesting question, which is, can a particle exert a force on itself? So here's an electron, and let's imagine this electron is in outer space, not near anything. Does it exert a force on itself? Well, what direction would it exert a force on itself in? Okay, we have a lot of issues trying to calculate a force, because first of all, the distance is in our equation. So the force is going to be 1 over 4 pi epsilon 0 minus E times, well, would it be on itself though? I mean, there's only one electron here, so why do we have two of these? The distance is 0, so this number would be infinite. R hat is undefined because there is no direction from something to itself. So the answer is, at a fundamental level, a particle can't exert a force, an electric force on itself. And it can't exert a gravitational force on itself for the same reason. It's where it is, and there's no other object with that mass. So there are a particle, these forces are between two distinct objects. A particle doesn't exert a force on itself. So we're going to be very careful when we're adding up net forces. And this is one of the reasons we're being a little compulsive about writing the force by the Earth when we talk about a gravitational attraction. Instead of saying just force gravitation, we're going to count every object in the surroundings once and only once. And so that's one of the reasons that helps us do this counting. This idea of reciprocity, that gravitational and electric forces are equal, and between two objects are equal in magnitude and opposite in direction, leads us to a different way to think about the momentum principle, where if we take a system of more than one object, so we call this a multi-particle system because we're modeling these objects as particles, or a multi-object system. And so let's say we've got a bunch of objects that are attracting gravitationally, or maybe electrically, I don't know, whatever. And they've got some momentum, so this one has a momentum 1, and this one has a momentum 2, and this one has a momentum 3. And so the total momentum of the system is going to be the sum of the momenta of all the objects in the system. And if we choose our system to include all these objects and there's nothing else in the surroundings, that should mean that we can apply the momentum principle to this system. And so we should get change in the total momentum of the system has to be equal to the net force exerted by objects in the surroundings over some time period. And since that's 0, because there aren't any, we took all these objects to be, the total momentum of the system actually has to be a constant. And that's interesting because the particles are either attracted to each other or repelling each other. Let's say there's an attraction here, and let's say this one's positive, and this one's negative, and that one's negative. So we're going to have an attraction here And you can see why we draw forces with their tail on the object that's experiencing the forces, because once we've got a bunch of objects experiencing forces, we need to know what these forces are acting on. But this object repels that object, and it's attracted to the positive object, and this is attracted to that, and so there's forces acting on them. So in any time step delta t, we're going to get the momentum of object 2 is going to change, the momentum of object 3 is going to change, and the momentum of object 1 is going to change. But because these forces are equal and opposite, the sum of all the delta p's here ends up being 0, and p total doesn't change. It's a little easier to see with two objects, maybe a positive charge and a negative charge. They exert equal forces on each other in opposite directions. So we get an impulse F delta t here that changes, and we get an impulse F delta t here. The magnitude of the momentum increases, but since momentum's a vector, one is increasing in the plus x direction, one's increasing in the minus x direction, and the sum ends up being 0. And so we can write this more generally in what we call conservation of momentum. All right, we say the change of the momentum of a system and the change of momentum of the surroundings has to be equal to 0. And this is a useful principle in some situations, because if we choose everything around here of interest to be the system, then there's nothing in the surroundings. And so the momentum of the system, the total momentum of the system doesn't actually change. The momentum of an isolated system can't change. Okay, so coming back to some of your questions here. The question of, is a positive charge inherently attracted to a negative charge is really the same question as why is there gravity? Why is there's this electric attraction? And the answer is, what the answer physics gives here is, we observe that this is true. So we observe that in nature this happens. And therefore we think it's a fundamental thing, because the more we probe and the more we look, this seems to be fundamental. But note that in every case, looking at Michael's question, in every case, we're not talking about the force on, we're being very careful about system and surroundings. In every case, the force on an object in the system is due to an object in the surroundings. And we're dividing the universe into, we may do this multiple times, but we're dividing the universe into whatever we've chosen in the system, everything else is the surroundings. And then we're going around one by one, identifying every object in the surroundings and saying, how does that interact with the system? Let's add that up into our net force. And that's the power of the superposition principle, the fact that we can do that. The world would be very much more complicated if the fact that there were other planets in our solar system meant that the force the sun exerted on the Earth was not the same as it would be if those other planets weren't there. So the fact that we can actually do this pairwise interaction comparison is a very powerful thing. And it means that we can break this down and just add up interactions one by one between two identified, well-defined objects. Let's see what happens. I urge you to read this section in the textbook on conservation of momentum. This is the end of chapter 3. I'll put up another chapter 3 assignment today. And read that section carefully, because there's some applications of conservation of momentum that show you how this is useful, which we don't have time to go over today.